Okay, hybrid orbitals form something called sigma bonds. What the heck are sigma bonds? Sigma bonds are hybridized orbitals that form bonds. The sigma bonds form along the internuclear axis, or between two atoms. When they overlap end to end. And all single bonds are also sigma bonds. When I look at hybridized orbitals, there's sometimes electrons that are unbonded, or lone pair electrons. Lone pair electrons also exist in hybridized orbitals, but they're not bonding electrons. So let's take a look at ethylene. Ethylene C2H4. So the Lewis structure is shown on the left. Each carbon has two single bonds to the hydrogens, and there's a double bond between the carbons. So when we're trying to figure out hybridization, we first draw the Lewis structure to determine the geometry. Geometry can lead us to hybridization. If we know the hybridization, it can lead us to geometry. So each carbon has 3 bonds. So its geometry is trigonoplanar. If I have trigonoplanar geometry, the hybridization of that carbon is sp2. That means that one s and 2 of the 3 p's on carbon get hybridized. One hybridized orbital forms a bond between carbon and one hydrogen. I've got the same type of arrangement between carbon and the other hydrogen. So those are sigma bonds. They form along the internuclear axis between carbon and hydrogen. They overlap end to end. We can see the overlap right here. And they are single bonds. Same is true of the other carbons. So I've got one here and one here. Now, I've got these p orbitals, they're represented in blue here, that don't hybridize. I don't need them. But I have another bond between the 2 carbons. And that bond, turns out, is formed between my p orbitals that are not hybridized. And the lobe of the p orbitals above the axis and below the axis forms one bond. This is not 2 bonds, this is 1 bond. My second bond between the carbons is that 3rd hybridized part of the sp2 hybridization. So it's an internuclear axis between the 2 carbons. It overlaps end to end, so this is a sigma bond. So if each carbon is trigonoplanar, then it turns out my whole molecule is planar. Hybridization again for carbon is sp2. The second bond in the carbon-carbon double bond is just made from p orbitals. It's a pure p orbital bond. It turns out that bonds that are made from pure p orbitals are called pi bonds. So when I have multiple bonds, the second bond, the third bond in a multiple bond is a pi bond formed from pure p orbitals. Pi bonds are different. Pi bonds overlap side to side. They're formed exclusively from pure p orbitals, and when they form, they're above and below the internuclear axis. Or if I have multiple ones, I can also find them in front of and behind the internuclear axis. So if I look at a more involved molecule, like carbon dioxide, here's the geometry, the Lewis structure on the right this time. So I have 1 bond between carbon and oxygen. I have 2 bonds on carbon. So 2 bonds, that means my hybridization on carbon is sp, and the geometry is linear. So let's look at what's going on here in the orbitals. Oxygen has 2 pairs of electrons that are in hybridized orbitals, but they're not bonding. And then it's got 1 bond, a double bond, between the carbon and the oxygen. So oxygen hybridization is sp2. So it is going to be trigonoplanar. So if we take a look at oxygen, because it's sp2, there's 1 p orbital that doesn't get hybridized. 3 orbitals are hybridized. So here's an orbital that has a lone pair of electrons in it for oxygen. Here's another orbital that has a lone pair of electrons in it for oxygen. 3rd hybridized orbital forms a bond between oxygen and carbon. It's a sigma bond because it overlaps end to end. It's got the same thing mirrored between the other carbon and the oxygen. So the 2 hybridized orbitals on the outside have the lone pairs. The 3rd hybridized orbital overlaps with carbon's hybridized sp orbital, and we get the sigma bond. So here's the end-to-end overlap. Oxygen has 1 p orbital that's pure. Carbon has 2 p orbitals that are pure. So on the one end, let's look at the right-hand side first, it's a little easier. The p orbitals that are vertical on carbon and the p orbital on the right-hand oxygen form a pi bond below and above the internuclear axis. So there's my second bond between carbon and oxygen. Sigma bond's one, pi bond is the second one. On my left-hand oxygen, the orientation switched, primarily because of where the p orbital is on the carbon. So the other p orbital that isn't hybridized on carbon is not vertical, it's horizontal. It's coming towards us and it's going away from us in this three-dimensional arrangement. So that means that the p orbital that bonds to it on oxygen's got to have the same orientation. So one part of the pi bond comes out towards us, the other part of the pi bond goes back into the board, and so there's our second bond between oxygen and carbon on the left-hand side. So one pi bond, one sigma bond between the carbon and oxygen on each side. And multiple bonds always have at least and exactly one sigma bond, and more bonds than that are pi bonds. Okay, this is the structure of benzene. So each of the points here is a carbon atom. So the lines are sigma bonds. So we have 1, 2, 3 sigma bonds for each carbon, so it's an sp2 hybridization. Each of the 6 carbons is the same. Hydrogen just has an s orbital, it doesn't hybridize. So the s orbital of hydrogen overlaps with the sigma sp2 orbital from carbon, and we get a sigma bond there. Same is true for one bond between each of the carbons. Each of the carbons has a single p orbital that doesn't hybridize, and they're all oriented the same way because benzene's a planar molecule. What happens now is, because these p orbitals are all in close proximity to each other, is we have them essentially connecting along the top and connecting along the bottom. They overlap side to side, so they are essentially flopping back and forth continually, allowing the electrons in them to move wherever they want to. So when it's drawn, it looks like donuts. So if we're going to draw benzene, we can draw it a couple of ways. If we draw it without the hydrogens, because we understand that they're there, it's going to be a 6-carbon ring, and one way we can draw it is having double bonds every other place. The resonance structure would be to move the carbon double bond to the alternate sites. So there's the resonance structure for benzene. A more common way to do it, though, and a whole lot easier way to do it, is to just draw the hexagon for benzene and a ring inside. And that ring shows the electrons in the double bonds are delocalized, and so they can go amongst the 6 carbons uniformly. Okay, when we're trying to determine hybridization for a molecule or an ion, first thing we're going to do is determine the electron pair geometry. So I'm going to go to Lewis structure. Mainly of the central atom, but we may need to know it for all the atoms. So we draw the Lewis structure, we determine the number of bonds on the central atom, and then we figure out how many lone pair electrons are surrounding that central atom. That will help us figure out the hybridization. So when I hybridize orbitals, it makes the bonds equivalent in energy and in length. It minimizes the overall molecular energy. So let's take a look at a couple of them and see what happens. Okay, let's start with ammonia. Ammonia is pretty easy. Electron pair geometry. So nitrogen has 5, hydrogen has 3 valence electrons, so we have 4 pairs. So draw the Lewis structure. Nitrogen in the middle, 3 hydrogens attached. That takes care of 3 of my 4 pairs. The last pair is a lone pair. There are 4 pairs of electrons associated with the central atom, so the electron pair geometry is tetrahedral. Because I have 4 pairs of electrons associated with my central atom, my hybridization is sp3, because remember, lone pairs are in hybridized orbitals. Phosphorus pentachloride. Phosphorus has 5 valence electrons. Chlorine has 7. So 7 times 5 is 35, plus 5 is 40 electrons, so I have 20 pairs. First thing I'm going to do, again, is draw the Lewis structure. Phosphorus is in the middle. I form 5 bonds. So there's 5 out of 20 pairs. Now I put in the lone pairs around chlorine. So that gets me 20 pairs of electrons. Because I have 5 pairs of electrons on my central atom, my electron pair geometry is trigonal bipyramid. Because I have 5 pairs of electrons on my central atom, my hybridization is dsp3. One of the things we didn't talk about is when we're drawing Lewis structures and we need to draw them in 3 dimensions. The convention for showing an atom or a part of the molecule coming towards us is to draw this triangular wedge coming up towards us. The convention for showing something going back behind our sheet or our page is to draw a dotted line. So the chlorine here is behind the page, the chlorine here is coming out towards us. Okay, our last species is sulfur trioxide. Sulfur, 6 valence electrons, oxygen, 6 valence electrons. So 4 times 6 is 24, so I have 12 pair. Sulfur is the central atom, so it has 3 oxygens attached to it. Now I put in the lone pairs. If I were to put 3 lone pairs on this last oxygen, then each oxygen would have an octet, but sulfur would be deficient. So I'm going to keep that in mind as I'm throwing them in. So I have 1 more pair of electrons that I need to put in. If I put it as a double bond between this oxygen and the sulfur, then both that oxygen and the sulfur have an octet. Everything's happy. I have resonance going on. So if I were asked to, I would need to draw the other 2 resonance structures here. But I can still do the geometry and the hybridization with just 1 resonance structure. So my electron pair geometry, I have 1, 2, 3 bonds, is trigonoplanar. Because I have the trigonoplanar geometry, my hybridization is sp2. There is some more information in Chapter 9. We may talk a little bit about paramagnetism and diamagnetism, but that's not something that the AP is discussing anymore, so we're just going to not add it to our list of things to do. So this takes us through 2 chapters, Chapter 8 and Chapter 9, looking at the bonding of molecules and the geometry associated with that bonding.